Inside there is bus again, multiple bus, whatever. Let's say it jumps from here or something. And then you have your cities, energy cities that hook up into the meter. Then you take power again, and then you can do it in a multiple different way. But the idea is to connect in parallel with DEWA grid. Okay? So as you know, DEWA works like this, and this is typical also. All right? There is a transformer here that is DEWA property. This transformer could be different levels, but usually for industrial customers like yourself, you will have 11 kV by a 0.4 kV, and the transformer is rated to 1,500 kVAs. All right? So this transformer delivers into a main breaker, which you guys know it as ACB. And ACB because of the rated power that they do have, all right? Because usually this power, if there is a short between phase and neutral or whatever, or phase to phase or whatever, then you will realize that the amount of current that they generate is very close to the 2,500 amps that you will put here, okay? Again, so this is only for your information, general information, but here you have bus bars, correct? Phase 1, phase 2, and phase 3. So far so good, right? And then from here, you take for load 1, let's say big load, I want to say 800 amp load, for example. Breaker is there, of course, connected here, again. And then here you have multiple and small, let's say 200, 400, and I don't know what else, 640. And this goes to load 2, load 3, and load 4. Okay? But this does not have solar. This is your stuff without solar, right? So our challenge here in this project was, okay, we need to bring solar in parallel. So by bringing solar in parallel, we need to extend these bus bars. Okay, we extend the bus bars and we put our solar breaker, what you call solar incomer. Okay, and our cables comes from here, and from here we are again hooked up. If you put this breaker on, the frequency and the voltage that are here now, DEWA, 50 Hertz, will be along to our inverter level. All right? Are you with me? Clear? So your contract with DEWA now says that you guys will buy DEWA the amount of energy that they bring to you, but there is other small letters over there. You also contracted for DEWA that they have to guarantee the 400 volts and 50 hertz, all right, in a steady quality base. This is called power quality, okay? Because if DEWA does not give you this, probably your LED lights will, or your chiller will complain, or your compressors will stop for safety. All right? I will give you an example like this. Okay, so now you know what's happening here. Now I will make here from the solar panel, solar string. This is one solar string. So 1 plus 1 minus. Okay, so this is 20 panels. Don't forget. Okay, and 6.5 kilowatt peak, and we take it here, we multiply these, how many times you remember? 18. We multiply these 224 times, all right? 18, yes, for an inverter, okay. So let's say for an inverter, okay, I'll do that, maybe it's better. I'll just clear this. So per inverter we are putting 18, right, Raul, you said? inputs, okay. And how much it goes, Raul? This one? 6.5 times 117. Okay. Then we deliver these 117 here to your inverter. Multiple of these, right? You have 17 units of this coming into one machine. Then we have 13 machines. This is number 1. Number 13. Then these ones move out, goes to a combination panel, and the combination panel is nothing more than paralleling stuff again, okay? And then we take it from here to a meter cabinet. That goes now, let's see if I have space. Okay. Remember this panel from before? The DIWA one? This comes from a transformer. Okay. Your bus bars. And then let's say you have here already your solar. This goes for chiller 1 and chiller 2, okay? Yeah. Chiller 1 and chiller 2, for example, okay? And this is our solar, okay? Meter cabinet here, all right? Since we don't have Wi-Fi power available at these capacities yet, we need to use cables, unfortunately. Okay, so this is how energy is coming up now. You're generating DC current up to here. Okay, this is DC up to here. From here, the inverter changes the games to alternated current, AC. We use the same concept as we used before, series and parallels and all that stuff, and combine here on the AC combiner. Okay. And then from here we deliver into a meter cabinet with an isolator and then put it back here. Let me just give you some numbers. We are putting 117 kilowatts DC into an inverter, but we know that it only gives you 100. So why usually we do this? Because there is energy losses throughout the way. There is dust in the panels. There is voltage ohmic losses, right? So we account for a little buffer on the DC side to make sure that when you buy the inverter, you are buying something that you're going to use or planning to use. So that will give you the 100 kilowatts. But Ruben, can you tell me how many amps is 100 kilowatts? AC? Or I'll do it right here. Just. So it's 144 amps. All right? So imagine now if I have 144 amps coming here, this breaker should be enough to cater that power, right? So it does not trip, okay? But then, in an easy way, if I have 13 machines, then this combination panel, this breaker, I have 144 times 13. So the outgoing in amps in the steady conditions, perfect conditions will be 144 times 13 times 13. So will be 1,878 amps. This is not our system, okay, guys? This is just for you to understand what is the amount of current that is flowing. Therefore, the cables are designed accordingly. This breaker has to take at least, let's say, 2,000 amps, because if you ask someone to give you a breaker of this, no one will give you nothing, right? You have to go up. Then this isolator should be the same rating of this, and then this breaker should be the same rating of that, all right? But this is a huge amount of energy, a huge, all right? Great. So there is...
Phase converted into 3-phase?
Okay. Yes. So, okay. Let me use this space here.
So are there 3 different circuits?
Yes.
Single phases?
Yeah. exactly. So when you purchase the inverter, is by nature a three-phase inverter. But by default, a three-phase system is built up on a L1, L2, and L3. L3, okay? So, and then if there is neutral or not. So if you put the meter from L1 and L3 and neutral, you should have here. Yes, but if you put the meter from L1 and L2, put a triangle here now, then you should have the three-phase system. All right? And if you have a ground, what is the value that if I'm at L3 and ground, for example? 230. So if I have a circle here, and if I measure these two, okay? But yes, electricity is built up like this. The secret is paralleling, series, and all that stuff.
So in this inverter, which is three-phase, the supply given is, the entire supply is provided, and then inside it, with the help of IGBTs, it is converted into three-phase.
Exactly. So let's talk a bit about that. That's one. So I'll come back to this one. I'll go to slide 8, and let's talk a little bit about inverters. Yeah, that's important, Sumit. Yeah. Okay. So a DC graph. If you put an oscillator on a DC graph, if you put an oscillator on an AC graph, and this is electricity. Okay. If you put this is 0 volt. Okay. If you put an oscillator on a DC current, what are you going to see? You're going to see this, right?
Yeah.
It's a direct current. But if you're going to put an oscillator on an AC system, single phase, you're going to see this. Okay? It's a peak value from here. Then you have your frequency here, right? Sorry, your frequency is not here. Your frequency comes here. All right? Ooh. Okay, I'll make it again. So this is your current curve. Then you have from 0, 1 cycle is your 50 hertz. Okay? And here you have the amplitude of these will be 230 volts. Okay? So if you start heading curves like this on this side now, you'll be able to measure 230 volts plus a piece of it in the graph. That's why you have 400s or 380s or whatever. Okay? So, now, what is inside this machine? Right? So, beside the fuses for protection here, all the strings that you are bringing, right? Then, it's another game of paralleling currents, right? I told you guys before, if I have 15 pieces, so 1 and up 15, and each one is, let's say 9 amps, 9 times 15 will be 9 times 20, 45, 135? 135 amps. So when the inverter is getting 9 amps, 9 amps, 9 amps, 9 amps, but the machine then combines them, all of them, into a 35 amp output that will deliver to the AC side of the system. Okay? Here we don't need filters. We don't need nothing. But what is coming here is this. Now we have to convert this into this. All right? So what this guy does is that game. So oscillators, filters, in order to make sure that your power electronics are kind of steady. All right? So then that power is divided into 3 phases.
Okay, each inverter gives 3 phases.
Yes. So, actually, if you want to run this system, you could run in a single-phase system. For example, you can take this phase to a separate load, this phase to a separate load, but those loads should be single-phase loads.
Yeah.
All right? Since DEWA delivers to you in a 3-phase system, right? DEWA delivers to you in a 3-phase system here. Okay? So that's why we hook the 3 parts of it. Okay? So what is important also to know here, because Sumit, you talk about IGBTs, and that is a very nice observation. Solar panel, very basic, inverter, and grid. Okay? So, there is more stuff in the middle, okay? But how do we know that the system works? How can I tell you, guys, your system has now been connected for a week, for example. How do I prove you that this system is working, right? Because that question comes up also. So we can prove to you that the system works by the following reason. And one component of that justification comes from these IGBT. So IGBT is a very small diode component bridge plate that protects you from the grid. And at the same time, allows you to synchronize with the grid. That's a very smart device. That's the heart of the inverter. So the IGBT, what does is this. If the grid supplier gives you this voltage and this frequency at this point, okay, IGBT will know, okay, so therefore, it will receive the DC side voltage and amps, okay, and if everything is stable here, it will be able to match and synchronize without you touching a single button. That's DC synchronization is done by the IGBT. The order is done by IGBT. So if you fail one of these, if it goes 60 or if it goes to 100 or something, then or if it goes dead, this guy will also know, I no longer have these values, so please unhook from the grid. Because if I don't know what is the values, I cannot generate anything. I don't know the reference. This is the reference. Okay? So far, so good? That's how the IGBTs comes. But this is basics electricity from 90 years back. Electricity didn't change much. What changed was that these smart machines and power electronics, that has been evolving. But the main core from these gentlemen here until how you built up electricity is still the same today, from 90 years back. Of course, technology changed the breaker sizes, changed the protections, all that stuff changes. But the concept is the same.
Just need to know what in case, what is the protection it has in the cases of surge? Because I will tell you what the problem with what Deva is. If you see in most of the, this is an industrial area, where it is come to like marina area particularly, it's a linear load basically, all buildings are there. And Deva's grids are not that capable. So wherever they switch on to these ringman units, it generates a surge. If you remember about a year back there was a fire in Marina. Okay, these guys, so they disconnected the supply, and then when they restored it, they didn't take care that stepwise buildings are charged. They just put on, and it brought a surge. Literally, one of the bus bars has got burnt
problem
of this. So in such scenario, because basically I will tell you, Deva is not a technically sound organization. It's a truth. They run by their grace of God. They don't run by nice engineers. Okay, and the technicians are there are horrible. So a surge is a big problem here. When your frequency will change suddenly, if your frequency shoots up, then have we put any mechanical device before this which will protect us?
Yes,
do we have
you do have. Yeah. Okay.
That will protect my this.
Your facility, let's say.
Yeah.
Okay, so there is what we call. Okay, so let's go back here. This device, by default, will allow you to protect your solar system from these effects. Okay, voltage dips, surges, short circuit currents on the grid side, all that stuff. So the IGBTs are coming inbuilt here. That's a feature of on-grid inverters. So if you don't have anything else, your solar system will be protected by, when this goes crazy values, okay, so the reference is this, okay?
Yes,
but the machine knows that it can go, for example, 400 volts plus minus 5 volts. And the frequency can go much more tighter, let's say, plus 0.2 hertz. Okay? So until your grid jumps out to 55 hertz, all right, IGBT will not do nothing. Okay, so if DIWA in a certain moment by your neighbors are off and they're ramping them up and the load changes voltage to the power plant and the frequency comes back again at 50.2, your system will remain the same. But if that frequency comes 53, this guy will say stop everything.
Okay.
Isolate from here back.
Okay.
Okay?
Okay.
Okay?
So
So IGBT protects that. But DIWA, when the consultants wrote the regulations of DIWA, they had another IGBT as a redundant feature. And that comes here. And usually people calls interface protection. We will see this running, okay, later. Later, yeah, not today, but we'll see this running, okay? And what is the concept of this machine? Is to replicate the IGBT feature, but does it on a voltage and frequency, okay? Voltage and frequency.
Okay, so
So,
this is also there.
yeah, so this guy is sensing what is the voltage in each line and what is the frequency on each line on the DIWA side.
Okay.
Okay, and is also matching, is also sensing what is being produced by your inverters.
Okay.
Not at this level, mainly at this level here, at this level. Because whatever comes from here is the combination of these, right? So it's measuring from here and it's measuring from here. Okay? By comparison and by the setting up the interval, what is the setting up this interval here, this is set up on this interface protection, then we know that the machine is also sensing that values. By sensing the values, if by any reason a value jumps off, okay, or goes above, over or under, this machine will also actuate by opening the motorized breaker. Okay? It opens the circuit. So if it opens the circuit, you no longer have the 400 volts, so everything stops again. All right? And if the frequency goes above or under, then also senses that information and then also opens. But this is a motorized in the sense that if the conditions are restored, it will automatically close the circuit again so you guys can synchronize again. If this order, the first order, this is the first order, is not acknowledged in a quarter of a second order will come to the other breaker, solar breaker here. A second order will come to the solar breaker, like a shunt trip. And that to open this machine. But if this one opens, this one needs to be manually up. But if it opens, like an operation team, for example, you will know that this guy did not respond. So you may need to see or call someone to come and see the problem if there is any issue here. Okay. But that's your protection. But again, this is not over current protections. This is over voltage and frequency protections. Over currents is a problem, but I agree with you, Sumit. But let me try to give you some peace of mind, right? This is Dubai, all right? Dubai has 12 gigawatts of power plants. Jebel Ali power plant. I don't know which power plant. The total combined is 12, all right? This is Dubai. And you are here. This is your stuff. This is here, right? And here you have 1.3 megawatt AC. So this is 12,000 megawatts, okay? Supplies full over Dubai. And this is your capacity here in your roof, okay? So this is less than 0.1%, right? So if you are the only guy with solar systems in Dubai, okay, you will not be able to touch that power plant. But I agree with you. Now imagine that Marina is this amount of a power request. I don't know. Let's say 2, or let's say 3 gigawatts, right? If they shut down the medium voltage substations to kill the block entirely because there is a fire, there is whatever is coming up, I don't know. Then when they bring this live and the output is people requesting power, what will happen to the power plant? Now this is a power plant of Jebel Ali power plant, it's close to Marina, okay? Jebel Ali power plant is one of the biggest in the world, it's 5 gigawatts, okay? Probably you are connected from here to Jebel Ali power plant through one of these medium voltage substations, okay? So what's going to happen here, Sumit, is this. Okay, and this is the power plant. Now there is medium voltage substations that converts, let's say, the 400 kV to 135 to 132 or 63 or 32 or whatever, until you reach the block of the buildings in the marina, right? And these guys are requesting 3 gigawatts, okay? And the power plant can give you 5, okay? Let's say this and then there is small minor ones until you reach here to the transformer that supply this building. And then here you have the users pushing AC chillers, pushing sockets, pushing cooking stuff, right? Okay, and by physically, DEWA protects themselves by saying, okay, Dubai Marina cannot take more than 3 gigawatts, where should I take these 3 gigawatts? But if power plant of this one, the 5 gigawatts in Jebel Ali, can supply fully entire marina easily, all right? But that cannot supply the rest of Dubai. Remember, Dubai is 12. So DEWA has to manage multiple of power plants, one here, all right, on this, and all are interconnected somehow, okay? So therefore, and the problem comes on Sumit, now reaching to the problem that when someone comes to the substation and go to the feeder of Marina, let's say not here, but you have a feeder for 3 gigawatts here, for example, hypothetically, okay? And someone puts these 2 or 3 breakers up, so these guys will have power at the exact same time. What will happen is this. The people in the DEWA room that are managing the power plants, right, now I'll put them guys here, okay? These guys' objective is to make sure that the generation is at every single moment equal to the load, okay? Load equal generation implies that voltage and frequency, okay. If the load equal to the generation, means if the load, 3 gigawatts matches 3 gigawatts from here or any combination possible from here, your frequency will be matching, all right? But we are talking on a millisecond, someone asks for 3 gigawatts. And that creates imbalance. For example, loads below generation. So if the loads are below generation for a certain amount, then your frequency will be out of range, will be crazy. If the loads bigger than the generation, your voltage be crazy. Of course, when you run chillers and sensitive machining and LEDs and all that stuff, then this could have a crazy impact. And if the values are for amount of time are, because you cannot sustain this for a huge amount of time. I'm talking seconds. We are talking seconds, okay? If DEWA says loads below the grids, below the generation for 20 minutes, this value will be crazy, the grid will shut down. You have a full black shutdown, like happens a lot in Africa, so in India also a lot of shutdowns, right? Because there is more demand than supply, or because there is more supply than demand. But in developing countries, this become a big issue because then you are the owner of DIWA. So you can go back to them and say, guys, you damaged my chiller or my sensitive manufacturing equipment, my medical stuff got also problems. So you can enter on these agreements with DIWA. But that's how a grid in general terms works. So if this is on a cycle, on a monthly cycle now, what does it mean? Means that during this month, you guys didn't import much energy, you export energy. So this amount of energy goes to your account and credit on the next month. Okay, so your bill, your DIWA bill will change format. After 2 months, when the harmonics are okay, and the grid is stable, they usually take 2.5 months. Next cycle, they change your energy bill to a solar energy bill, where you'll be able to know how much was the export, how much was the import, and the delta roll over. But since you have 2 points of connection here in your system, okay, what's going to happen is that then you have 2 solar bills. Okay? Clear? Clear? This is on a daily cycle, this is on a monthly cycle, but the concept is the same. It's the total lump sum that you export and the total lump sum of import that will be matched. It's not on a daily cycle. DIWA doesn't care about daily cycle. They care about monthly cycle. And they send you an invoice for that. Okay?